Alright, today we're going to go over probability lesson number 3. And this is probably what you know about probability from 8th grade. We did some other things first in this chapter, but hopefully you'll see by the end that there was a reason why we went in the order that we went. So let's just jump right in here. Probability is pretty much just the chances of something happening. So for instance, the first example I use is if you're watching a basketball game and the player is shooting 80% from the free throw line. What that means to me is you could probably say there's an 80% chance that he will make the next free throw. You could also call that 4 out of 5. Or you could also call that 0.8. So hopefully what you get out of that is you can write probability as a percent. That's what that 80% was. Or as a fraction. So that would be 4/5. Or also as a decimal. So you could write it 3 different ways. The key here is that you need to remember a probability cannot be less than 0 and it cannot be greater than 1. So when you hear an athlete saying they gave 110%, that's not physically possible. Always drives me crazy when I hear that, but whatever. They can say what they want, I guess. It's a cliche, so whatever. Anyway, so the official definition is not a big surprise. You take the number of favorable outcomes and divide it by the number of total outcomes. So let's say you're playing a game with dice and you need to roll a 1 to win. Well, out of the 6 total things that could happen, rolling a 1 would be good for you. So the probability of you winning would be 1 out of 6. Now, what if I said I have the dice and you need to roll a 1, 2, 3, or 4 to win? Well, then your probability, you still have 6 total outcomes, but this time 4 of them are good. Because if you roll a 1, 2, 3, or 4, you win. So in this case, you would actually reduce that and you would say that your probability of winning the game is 2/3. So that's how probability works. You've seen that part of it before. We'll get a little bit deeper into the complicated parts over the next few minutes, but that's the basic idea. You can get questions right sometimes just with the basics. Let's move on here, and this is the point I was trying to bring up before. Why did we have to learn about the fundamental counting principle? Why did we have to learn about permutations? Well, it all fits together. And the way it all fits together, one of the ways it all fits together is when we are dealing with what are called compound probabilities. All right, there you go. Compound probabilities. There you go, it's spelled right. Compound probabilities, they're just like regular ones. The only difference is they involve multiple parts. As in, what is the probability of this, and this all happening at the same time? So type number 1 is independent events, and that's a phrase we already learned. Independent events are when one thing happens and another thing happens, and one event does not change the probability of the next event happening. So for instance, if you flip a coin, you have 2 options. You have heads and tails. And if you flip it a second time, you still have 2 options, heads and tails. No matter what you do, no matter how many times you flip it, you always have 2 options, heads and tails. So question number 1, what is the probability that you will flip a coin 3 times and land on heads all 3 times? Well, the first time you flip it, there are 2 things that could happen. The second time you flip it, there are 2 things that could happen. The third time you flip it, there are 2 things that could happen. I think you get the idea. We want it to be heads all 3 times. So what is the probability that it will be heads the first time? 1 out of 2. What about the second time? 1 out of 2. What about the third time? 1 out of 2. And with compound probability, all you have to do is multiply each part. So you look on top. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So the probability that you will flip a coin 3 times and land on heads all 3 times is 1 out of 8. That's how compound probability works. Okay, so your odds of getting heads, your probability, I should say, of getting heads. Sometimes people use odds, but that's a different conversation. Your probability of getting heads doesn't change with the number of times you flip it. It's still 1 out of 2. If the question said all 5 times, you would just do it 5 times. Question number 2, you must flip a coin twice. Well, we already know how to do that, so 1 out of 2. And then if you flip it again, it's going to be 1 out of 2 again. And then roll 1 die. What is the probability that you will flip heads twice and then roll a 6? So when you flip a coin, there are 2 possibilities. When you roll dice, how many possibilities are there? Well, you got 6. Out of those 6 possibilities, how many of them are good? Well, only 1 of them. Rolling a 6 is the only possibility that you want. Rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5. Those don't count. We want to roll a 6. So out of the 6 things that could happen, only 1 of them is good. Okay, so you set it up like this. Your probability of getting heads is 1 out of 2. Your probability of getting heads the second time, 1 out of 2. And then your probability of rolling a 6 is 1 out of 6. Multiply that together and you end up getting 1 over 24. And for those of you who are into percents or who have your calculator out, that's about 4%, give or take. Maybe about 4.2%, give or take. Question number 3. I am thinking of a random letter and a random number. What is the probability that you will guess both correctly? How many letters do I have to choose from? 26. Remember that. I've had people ask me in the past how many letters are in the alphabet. I ask a lot of questions about it, so just remember 26 if you don't know that already. Now, I should have been more specific here. Where it says random number, I'm thinking random digit. So let's change this. In fact, when I print out your notes, I'm going to change it to digit because I want to be more accurate. Anyway, I'm thinking of a random digit. Now, when I think of digits, that's like when you're looking on your cell phone, when you're trying to dial someone's number. How many digits are there? Well, you have 10 to choose from, 1 through 9, and don't forget the 0 on the bottom. So, I am thinking of 1 random letter, so your probability of guessing my random letter is 1 out of 26. Your probability of guessing my random number is 1 out of 10, my random digit. I'm sorry, like I said, I'm going to change that. What is the probability you will guess both correctly? You multiply it and you get 1 out of 260. And that would be the probability of it happening. So hopefully you see the similarity between the fundamental counting principle and probability. You're still figuring out how many ways something can be done, and you are still multiplying. You're just making a fraction involving the total number of possibilities. All right, here's the next type, and this is for dependent events. And this is when one event does change the probability. One event changes the probability of the next event happening. All right, here's another typo. I'll fix this as well. This is going to be question 4 on your note sheet. Wow, I am on a roll today. Your friend is holding 10 index cards numbered from 1 to 10. You draw a card, and without putting it back, you draw another card. What is the probability that both are even? Let's talk about the first draw and then the second draw. When you draw for the first time, there are 10 index cards there. Okay, they are numbered 1 to 10, so just on the side, let's visualize it. I know this is cheesy. Do it anyway. Write it out from 1 to 10 because it's a good demonstration. All right. What is the probability both are even? Well, what is the probability that you drew an even right off the bat? Of the 10, 5 of them are even. 2, 4, 6, 8, 10. Now, what is the probability both are even? Well, in this case, take a look at that second draw. You didn't put back the first card, so now you only have 9 cards to choose from for your second draw. You don't have 10 cards anymore because you didn't put back the first card. And you drew another one. What is the probability both are even? Well, if you drew an even on the first one, let's say you drew the number 8. How many even cards are left? It's actually only 4 now. So that's a tricky question. This is similar to permutations, where the number in the blank goes down by 1 every time. As soon as somebody wins the race, that person can't finish second. It's got to be a new person. Same thing here. You didn't put the cards back, which means it's a new card. So there are only 9 cards left. So when you multiply here, you're going to end up getting 20 out of 90. And I'm going to be lazy about it. I'm just going to take off the zeros, and I'm going to call the answer 2 over 9. If you were punching it in the calculator, you would get 0.222222, so 22.2%, yada, yada, yada. But that's how it's going to look. Okay, so this is how dependent events behave similar to permutations, because the number in the blank is going down every single time. Now, if you ever wanted an example of combinations in probability, that would be, what are the odds of winning the lottery? What is the probability that you will win Powerball? And then prove it. That would be an example of using combinations to help you. In fact, those of you who are listening, that should be your email question. I had a couple people get the last email question right for extra credit. Let's see if you can get that one right. Don't just tell me the probability of winning Powerball, winning the jackpot, but tell me how you did it. Tricky, huh? Well, if you want extra points, you're going to have to earn it. All right, real quick, let's talk about these examples on the back. I think these would be a really good thing to talk about. You have an equally likely chance of spinning any value on the spinner. Find the probability of spinning the given event. Number 1, a shaded region. How many regions are there total? 4. How many of them are shaded? 2. 2 over 4. I do not like the way that's written. Let's call it 1/2. If you called it 50%, good for you. If you called it 0.5, good for you. Number 2, a factor of 27. That means a number that goes into 27. So like 1, like 3, like 9, like 27. Those are all factors of 27. So out of the 4 numbers that are on the spinner, how many of them go into 27? 1. The number 9 is the only number up there that is a factor of 27. So that is the only option, 1 out of 4 chance. All right, a number less than 6 or a shaded region. Less than 6, less than 6, less than 6. This is not less than 6, but it says less than 6 or shaded. It's not less than 6, but it is shaded. So the probability of you doing one or the other is actually 100% because all 4 of your options are one or the other. So 4 out of 4. I don't like the way that's written. Let's just call it 1. An even number or perfect square. Even, even, perfect square. 3 squared is 9. 5 is not even, and it is not a perfect square, which means it doesn't count. So the probability of that happening is 3 over 4. All right, a prime number. To be prime, the only number that can go into a prime number is 1, or itself, you could say. So for problem number 5, 2 is prime because 1 and 2 are the factors of 2. That's it. 4 is not prime because 2 times 2 is 4. 5 is prime. 9 is not prime. So it looks like I have 2 options out of the 4. So 2 out of 4. I don't like the way that's written, so let's call it 1/2. And I love question number 6 because people ask me about it all the time. What is the probability that you'll spin a 2-digit number? No, can't do it. There's no chance that you will do it. Anyway, finish the rest of this. It talks a little bit about independent, dependent. Some of those will be calculator questions because the numbers are going to get pretty big. Be ready for that. Good luck with it. Let's get an answer key up on the wall here in the next day or two, and we'll move on. Thanks for listening.